Hello everyone, welcome back to this course again. We are more than halfway past this mark, and today we are in this part of relations, as we have been studying about inductions, sets, even functions, and now we are in relations. Again, you can examine various parts of relations, various properties of relations in this first part of this lecture. So what is a relation? As we see what is a relation, you can also compare with that of sets as well as functions, particularly about sets. Let us see how they are related to one another. Okay, let A and B be sets. A binary relation R is a subset of A cross B. How do we define this? Let us say, for example, this set A be a students of CS major, and A is Alice, Bob, Claire and Dan, and let B be courses that department offers. Let that be CS 101, CS 102, CS 103, or it can be like we have here CS 101, CS 201, CS 203, 202 here. So these three courses of for bits for the set B. We specify relations R that equals A cross B as the set that lists all students that A is an element of A enrolled in class B, where B is an element of B. Got it? Well, now you have a binary relation in which R equals the set that contains these related elements. For example, Alice, CS 101, Bob, CS 201, Bob, CS 202, Dan, CS 201 and Dan, CS 202. As you can see here, you can clearly see that Alice is taking the course or the class CS 101, Bob is taking two courses, CS 201 and CS 202, Dan is taking one course as CS 201. Of course, Dan is taking two, the next one is CS 202. Right. So let us view it in more graphical ways. Let A be a cities in US and B be a cities in the states in US. So here we are going to have two different sets of A and B, which has cities and states. Say for example, let us say R to mean a city is a state in state B. So here A, for example, is the element of the set A. The small a, they are the ones that represents the elements, whereas the small b element represent the elements in the set B, capital B. Let us have here the following relations here. For example, the Philadelphia is in PA and Portland in MA, and this another Portland in Oregon state. So these VA, PA, MA, OR represents the states, and the Portland, Philadelphia, these are the cities in those states. So again, this can be of many different cities and states we can bring up. Most relations we will see deal with ordered pair of integers, though here we have deal with the pairs with cities and states. Let us go on further and see how you can represent these relations. So as I told you earlier, we can also use graphical ways to represent it. Okay, say we talked about this relations where Alice is taking CS 101, Bob is taking two courses, that is CS 201 and 202, Dan is taking two courses, CS 201 and 202, whereas Claire she has no relations. In other words, she is not taking any of these courses offered. Let's try to map these graphically and see their relations. Okay, here is it. Let's say Alice is mapped to CS101, Bob is mapped to CS201 as well as CS202, Dan is mapped to CS201 as well as CS202. As we can see here, Claire is not mapped. Moreover, we can also see that from Dan and Bob, there are two arrows emerging out. So if a two arrow emerge out from the same element, it is not a valid function, if you recall what is a function. And therefore, we can't just say that all relations are functions. As you can see, there is another reason why it is not a valid function is that Claire, there is no arrow coming out of Claire. So that also shows that this is not a valid function. Now you can relate functions and relations. By now you can also see what are the similarities with the set. Just keep these in mind. This can help you to contemplate on various other aspects and relations in this course. Let's move ahead and see the similarities and differences of relation versus functions. Not all relations are functions, but consider the following function here. Say here you have A is mapped to 4, B is mapped to 1, C is mapped to 3, D is mapped to 2. Well, this seems to be some kind of function, but that's also giving us clear relations in this example, this graphical examples, which means that all functions are relations, but all relations are not functions. Got it? You can see and examine, there are different types of functions we talked about, many-to-one function, one-to-one function, when function has one-to-one correspondence. In fact, we talked about inverse function. So take those properties and see how these properties come in line with the relations and what properties have more closer ties with the relations. That's for you to examine. Let's move ahead. So when we use which, like functions and relations, a function is used when you need to obtain a single result for any element in the domain. As you know that we have f of x as a function, and at times the function can be of an equation and you might need just a single result out of this whole function. As in terms of programming as well, you are expecting something similar. Like for example, like sine, cosine, tangent, these are all trigonometric function. A relation is when there are multiple mapping between domain and the codomain. So that's quite unique about relations. It can allow multiple mapping between domain and codomain. Like example, students enrolled in multiple courses. Yeah, that's one of the place where we go for relations. Now let's talk about relations on sets. A relation on the set A is the relation from A to A. In other words, the domain and the codomain are the same set. That's A here. So we generally be studying relations of this particular type in our course. So let's say A be the set with 1, 2, 3, 4 elements, which ordered pairs are in relations like R equals A comma B such that A divides B. So in that case you can write down the order with this condition. A comma B such that A divides B. So 1 comma 1, 1 comma 2, 1 comma 3, 1 comma 4, 2 comma 2, 2 comma 4, 3 comma 3, 4 comma 4. So this order has been developed, or this relation we have come up with is based on that condition A divides B from the given set 1, 2, 3, 4. So we know that 1 can divide all 4 like 1, 2, 3, 4, and 2 can divide 2 as well as 4, 3 can divide 3, 4 can divide 4. So that is how this whole map has been brought out, and as well as this table on to your right there also shows that the same relation. So you can see how this relation is getting along with that of the given conditions. Let us see one more example here. Consider some relation on the set Z or the following ordered pair interrelations. Let us say for example 1 comma 1, 1 comma 2, 2 comma 1, 1 comma minus 1, 2 comma 2. So say for example the relation R1 is A comma B such that A is less than or equal to B, and again R2 is A is greater than B, R3 is A divides such that A divides B. So as you can see here, we can bring out and check it out all these various parts in which A and B are applied. So as we move along, for example, if you look at R6, it says A plus B is less than or equal to 3. So this condition again you can see how it signifies the whole thing. In fact, onto your right, this has been gone one step down. If you go one step further, you can see here, for example, if you take this relation here, A plus B is less than or equal to 3. So this is A, this is B, which means like 1 plus 1 is less than or equal to 3. All these conditions it satisfies, but not this one. That is why you do not have here. Got it? So with that regard, you can see how this whole table has been mapped, and you can see how the relation has been established with respect to this given conditions from the given set Z. Relation properties. There are 6 properties of relations we will study, and these properties are quite interesting, as well as this can give us more information about how a relation would behave and on what conditions we have to come up with this particular relations. The first one is the reflexive relation, the second one is irreflexive, third one is symmetric, the fourth one is asymmetric, the fifth one is antisymmetric, the last one is transitive. Let us go one by one and see what they are. Reflexivity or reflexive or reflexivity is a relation is reflexive if every element is related to itself. So we have certain conditions. For example, A comma A is an element of R. So let us see how they are related and what operators will express this relations. For example, equal to sign, less than or equal to, greater than or equal to are the signs that implies this reflexive relation. And again, examples of relations that are not reflexive, which is greater than, less than. So this is the basic form of reflexivity or reflexive relation. Irreflexive or irreflexivity is nothing but a relation is irreflexive if every element is not related to itself. It is kind of opposite to the reflexive relation, and it is something like A comma A is not related to R. R represents the relation, right? Well, if you want to see more, if you go back, look at this property of reflexive and come here, and you will know that they are completely opposite of the reflexive. Irreflexive is just the opposite. Here examples of irreflexive relations is that greater than or less than, and examples of relation that are not irreflexive is that equal to, less than or equal to, greater than or equal to. Later on we are going to see how this whole thing can be expressed graphically. So at that time you can fully understand these properties. In the meantime, let us go ahead and see other properties. Here is, before that we will see some similarities and difference of this reflexive and irreflexive. A relation can be neither reflexive or irreflexive. So a relation can be neither reflexive nor irreflexive. Some elements are related to themselves, others are not. There are some conditions at which some elements are related to itself or themselves and some are not. So that can be possible. So we will see an example of this later on and see how in the same, for example, you have a set of elements and for a set, and you have another set of elements for another set. So particularly in one set some elements are related to itself and some elements are not related to itself, rather they are related to the elements in other sets in a different way. We will see that later on. Symmetry. As the word symmetry suggests, you can expect what a symmetry is. A relation is symmetric if for every a comma b is an element of R, or in other words the elements a comma b, they are part of this relation R, then b comma a is also part of R. That is the symmetric operation. So examples of symmetric relations would be equal to sign is twin of function in terms of programming. So examples of relations that are not symmetric is just, you could say, greater than, less than, greater than or equal to, less than or equal to. Yeah, basically symmetry means they are equal. So what is asymmetry? A relation is asymmetric if for every a comma b is an element of R, then b comma a is not an element of R. So you have two sets in which a is related to b but b is not related to a. That is the idea. So we will see later on some ways to express it graphically. At that time you will fully understand this part as well. But as the word suggests, symmetric and asymmetric, you can clearly see that for a symmetric, if a is related to b, then b is related to a. They are equal, whereas for an asymmetric, they are opposite of symmetric, and here we use symbols like greater than, less than, and examples that are not symmetric is just equal to, greater than or less than or equal to, twin of function. Antisymmetry. As we can see here, antisymmetry is a little bit different from symmetry as well as asymmetry, and this antisymmetry is not the opposite of symmetry. So you can clearly see what is the relation here. A relation is antisymmetry if for every a comma b is an element of R, then b comma a is also an element of R is true only when a equals b. So you can see that it seems to be very similar to symmetric function or in this symmetric relation, but with one condition in which a is equal to b. So antisymmetry is not opposite of symmetry. So that is what I want to emphasize, because at times students get confused with antisymmetric and symmetric because it seems they have similar property, but this condition signifies that they are different, the one in which we have A is equal to B. For examples of antisymmetric relations are equal to, less than or equal to, greater than or equal to. So these are the examples of antisymmetric relation. And examples of relations that are not antisymmetric, as you can expect, less than, greater than is twin of operator, the function. So as we have seen this three parts, especially like symmetric, asymmetric and antisymmetric. We could say that symmetric and asymmetric, they are opposite to each other, whereas symmetric and antisymmetric are not opposite of each other. Well, as we move on, let's talk about this next relation, before which we have some notes on the symmetric relations, because at times people get confused. A relation can be neither symmetric or asymmetric. That's possible. So for example, if the relation is expressed in terms of the elements A comma B such that A equals the absolute value of B, this is not symmetric. So you can recall the properties of a symmetric relation. So for example, -4 is not related to itself. This is not an asymmetric. Again, 4 is related to itself. So based on these definitions and conditions, you can see that there are at times the relation can be neither symmetric or asymmetric. So you can look and see that how asymmetric, antisymmetric and symmetric are similar or different. Of course, symmetric and asymmetric are completely opposite to one another, but there are in some rare cases that you have the properties that expresses the idea of antisymmetric. So here again note that it is an antisymmetric property. So even though one is related to another one, you get this idea. Then comes the property of transitivity. As we talk about this transitivity, I also want you to think back about this transitivity properties that we have come across in the past, because it's very similar to the ones that we have seen earlier. If you recall, there are times when we talk about when A is equal to B and B is equal to C, then A is equal to C. So this is similar properties of transitivity. So let's talk about it. A relation is transitive if for every A comma B is an element of R and B comma C is an element of R, then A comma C is an element of R. So that's the idea behind this transitivity. That's like if A is less than B and B is less than C, then A is less than C. Got it? Yeah, that's quite simple. Thus less than is a transitive symbol. So if A is equal to B and B is equal to C, then A is equal to C. So you can say that even the equal to is a transitive symbol that represents the transitivity. So likewise, you can see more informations like consider is ancestor of function, and let Alice be Bob's parent and Bob be Claire's parent. Thus you have Alice as the ancestor of Bob and Bob is the ancestor of Claire. So thus you can say Alice is ancestor of Claire. You can see that grandchildren and grandparent properties developing. So thus a is ancestor of is a transitive relation in this example. You can consider another one is parent of function. Alice be Bob's parent and Bob be Claire's parent. Alice is parent of Bob and Bob is parent of Claire. So, Alice is not a parent of Claire. So, how is that? As you can see here, is parent of is not a transitive relation. So, Alice is Bob's parent and Bob is Claire's parent. So, we can say that Alice is parent of Bob and Bob is parent of Claire, but Alice is not parent of Claire. You know that because Bob is parent of Claire, not the Alice. So, the ancestor of function give us the transitive relation, whereas this relation is parent of does not provide us a transitive relation. Let us summarize this relation in this table and see what are the operators that signifies these relations. For example, reflective or reflexive, the operators that are used for reflexive is equal to, less than or equal to, greater than or equal to, and irreflexive is greater than and less than. Symmetric, just we use equal to sign. Asymmetric, greater than and less than. Antisymmetric, we use equal to, greater than or equal to, less than or equal to. And transitive, we use almost everything, right, depending upon the context. So, likewise you can see how these relations properties are related to one another and how they are different from one another and how these operators represents these relations. So, as we move on in the next lecture, we will see more informations on these properties with some examples. So, I am looking forward to see you in that section. Until then, have a nice time and goodbye.